Hello, I'm Adam Chapala. I'm a professor in computer science at MIT, and I'll be presenting our work there on formal verification. This is joint with Professor Arvind and a number of other members of our group, as shown here. So setting the stage here a little bit, my background has been more in formal methods for software, not hardware, and the received wisdom we always had in the software verification world was that those hardware people really have things figured out. They're actually using formal verification regularly in industry, and now I know that this isn't the standard verification technique, but it is used a lot more than software verification. The purpose of this talk really is to try to convince you that you should raise your standards for what you expect from hardware formal verification techniques. And I'll say a bit more about what we can achieve using some ideas borrowed from the software verification world. And I'll present our particular framework for doing that and tell you how we've been applying it to RISC-V designs. So here is the view of the hardware design process that I have as a relative neophyte to that world. We have some sort of generation process, whether it's Chisel or Perl scripts or whatever, that's going to produce some RTL code for us. And then we use a variety of CAD tools to get that down to the lowest levels of a workflow. So my understanding is that we have formal verification applied in many places throughout this picture, but they're sort of biased towards the lower levels of the way I've drawn things. And in particular, some of those little magnifying glasses are not quite at the top of the RTL box because there are a lot of properties of RTL designs that are not actually being proved too frequently in practice, and I'll say a bit about that. And we have almost no help from formal verification with getting the code generation parts right at the very top of this picture. So let me say a bit more about that. So typical hardware system is described hierarchically with a bunch of components, and we might want to convince ourselves of some property of one of the components. So let's pick that one out. And now we'll use some standard formal verification tools. Maybe we'll prove some invariants, write down some properties in some logical language, and try to demonstrate that they always hold at every point in the execution of the system. Or maybe we'll do some Boolean equivalence checking to take an alternative implementation of this same IP block and show that we get the same behavior. Neither of these ideas really matches our intuitive idea of correctness. So what I want to try to sell you on is the idea of actually formally proving that your IP block truly is correct. And in the setting of processor verification, one way to view that idea is we're going to take the ISA reference manual and formalize it, as the last talk by Nikhil said a bit about, and so turn that into a mathematical characterization of correctness and show that your processor really behaves the same way as the ISA spec in terms of allowable input and output behavior that the rest of the world outside the processor can see. Another way we might want to do things differently from widely used formal verification tools is, imagine you've done some kind of analysis and you've proved a property of one of your IP blocks. It would be nice if the story didn't have to end there, if instead we kept building larger and larger proved blocks by composing the proofs that we've done about the smaller pieces, ideally in a nice black box way, work our way all the way up to the full system, and then at this point we derive the kind of theorem that I was just talking about, showing that, say, your processor implements the ISA manual. So we don't want to just stop at isolated exercises using different tools with unclear formal meaning of what we've really done at a whole system level. Let's compose our results into big guarantees about larger and larger units. Another issue is, say, if you're verifying your cache coherence protocol and you have some particular topology of your memory system, you can do a proof about that one. Then the next day you decide to add some new nodes to the graph of your memory system, typically with, say, model checking. Now this means you're going to rerun model checking for the new version of your system, and it'll probably take longer because it actually tends to scale exponentially with the size of one of these diagrams, and things can only get worse as you scale up to more and more realistic systems. Even adding extra bits to the addresses that your system works with can lead to exponential scaling in the running time of model checking. So instead, what we're trying to suggest here is let's actually prove the theorem you're really interested in, which is for all possible tree shapes of your memory hierarchy, your algorithm instantiated to that tree shape actually does the right thing, say in terms of providing the abstraction of memory is a big array that you can read and write. So we want to do proofs like that. So this brings us to our system called Kami, which is a framework that we actually use not just to verify systems, but to implement them in the first place. And we use a high-level design language called Bluespec, or rather a variant of it we developed for this framework, and we automatically compile it to RTL. And we are building this proof support on top of a system called COQ, which is widely used already in the software verification world for results like the CompCert verified C compiler. And it's a very general mathematical reasoning engine, and we can use it to establish the gold standard of correctness for complex digital hardware components. And that's what this library is really all about. So let me give a review of the aspects of the Bluespec programming model that are important to understand how we go about making this verification problem feasible. The first thing is Bluespec, compared to Verilog, has some more in common with, say, object-oriented programming in Java. We break our designs into modules, but they're more like Java modules in that they have their encapsulated private state that other modules are not allowed to touch directly. Instead, each module exposes a bunch of public methods which can be called with arguments and can return values, and the methods can read and write the mutable state of the modules they reside in. And of course, modules are implemented by, or methods are implemented by calling methods in other modules, and they can in turn call others, so we get a nice modularity pattern here that makes it easier to think about how the system works, just like it does with object-oriented programming in software. Another key thing about this model is that in Bluespec, every method call appears to execute atomically, meaning that execution runs uninterrupted with no observable concurrency from other modules doing things at the same time. And what this means is when we run one step of execution in this atomic model, we can summarize that step as a trace of all the method calls that happen. Some of them are coming in to this module, so I'll write that as receive, and some of them are going out to other modules, and I'll write that as send. And each method call records the name of the method, the arguments, and the return value. And this is a complete record of all the interaction of this module with the other ones during one of these atomic steps. And now we need to decide what it means when we're going to prove the correctness property of a module. It's very important we're proving modules independently of each other so we can reuse those proofs to build larger proofs of larger systems. But what is the right theorem for a module in isolation? For instance, what is the right theorem for a processor core by itself? Well, the concept we use is that the specification for an implemented module is a simpler reference implementation of the same functionality. And we state the theorem by saying that the implementation refines the specification, which means any trace of interaction with the world that the implementation could have could also be replicated by the simpler reference model or the specification. And this is a very powerful concept that allows the implementation to reduce non-determinism compared to the specification, but not add non-determinism. Okay, so here's our module again, and I've listed two traces that involve a method call coming into the module, and then we also sort of delegate part of the work by calling out to another module with one of these send entries in the traces. The crucial thing that happens in this world to support modular proofs is that as we combine modules together to form bigger ones, from the trace that the rest of the world sees, we cross out all the purely internal communication steps. So as I take M and add N into one bigger module, we no longer need to record the calls to method H, which is part of N. This is now an encapsulated internal implementation detail. And in our framework, we've proved the general theorems that justify this way of thinking about correctness and that make it easier to reuse theorems about smaller modules to derive theorems about bigger modules. And I'll link another one in, and now the traces that we're exposing in this particular example only record, okay, you called this method with this argument and got this answer. We don't need to remember even which modules exist within the larger one that we're building. This is a key productivity enhancer for the engineers who need to do these proofs. So let's get a little more into what is the experience of using this system. I'm going to show some code here, which I won't explain in detail. Probably those of you who do a lot of chisel programming are used to the experience of showing someone the code in your favorite system and seeing a big question mark floating over their head. They don't quite know what's going on. Well, this is what our code looks like. It's also embedded inside a functional programming language, just like Chisel is, but instead of embedding in Scala, it's embedded in the language of the Calc proof assistant. And it happens to be the code for a method of DQ operation for a FIFO. And it's following the Bluespec model where when we do a DQ, we run all these steps in sequence with no observable interaction from anything else happening concurrently. More importantly, we actually do proofs about this code. So here's an example of some actual source code from one of our case studies. In this case, it's proving correctness of a processor which has 4 pipeline stages, and we say it's correct because it's giving the same behaviors as a processor that has only 3 pipeline stages. So the more optimized one is P4ST, and the reference implementation we're comparing against is P3ST, and we use the little less than equal for refinement, meaning behaviors of the first one can be mimicked by the second one. And we use a command called lemma, which is a standard command of the Calc system, and we're basically writing out sort of like the proofs we're used to writing in math classes, but they're in ASCII text, they're a formal programming language, and the steps we're taking are actually being checked algorithmically. So we get to benefit from all of the support that is standard with the Calc proof environment that we're using, including with several IDEs that are available. And now the experience writing these formal proofs is a lot like using Eclipse to write Java code. So when you're using Eclipse and you write some function call in Java, you might get a little red squiggle underneath the code you wrote, and that means something like syntax error or type error. When you're writing proofs in the Calc system, including with our library, you get a similar phenomenon where you write some step of logical deduction, and you might get the equivalent of red squiggles saying, the system didn't believe you. This is not a valid step of deduction. You better back up and reconsider your explanation. And any of these points here with the little bullets dividing the proof into pieces could be flagged in that way if something is wrong. And the particular steps here, like k-modular, k-refl, these are coming from our library of predefined proof steps that are going to be very common in the domain of digital hardware correctness. And we define them once, so you get to reuse them with a fairly high level of automation. But because of the way Calc is set up, you don't need to trust that we built them correctly, because each one of them generates a proof from first principles, just using the basic axioms of math and the semantics of the Bluespec-like language that we're using. And of course, the proofs of more realistic designs will be a lot longer than this one. But basically, the designer has to do some extra manual work to convince the system that the design is sound, because it is undecidable in general whether these complex kinds of IP blocks meet their specifications. We try to build a nice reusable support like this to make this as straightforward and fast a process for the engineer as possible. So then the basic story of what we're building with our Kami framework is, most importantly, it's a system that lets you write down designs and specifications for IP blocks, and then use our proof support. The primitive units of proof in a system like this are called tactics. So we provide a library of tactics for the most common kinds of arguments about correctness of systems, and we give you the tools to prove that designs refine specifications. And specifications are actually designs in the same HDL as the actual optimized version. So we have a unified concept of refinement that we use there. And because we're writing in this high-level Bluespec-inspired notation, we also need compilation down to RTL. There is a commercial tool suite from Bluespec Inc. that does this compilation for the original Bluespec language. We also have our own alternative open source compiler under development, not quite ready for wider use, but the key thing about that compiler is we're going to develop a formal proof of its correctness so that you know when you convinced yourself your high-level design was correct, and then you compiled the high-level design, the RTL that comes out is guaranteed to be a refinement of the specification as well. So you can get all the benefits of strong guarantees about RTL without having to do any direct reasoning about RTL. We encapsulate all of that inside the compiler for this Bluespec-like language, and this means that your design is quite close to the spec compared to what we see in more widely used kinds of formal verification that work directly on RTL. So let me give a little bit more detail, but not too much, about what exactly a proof looks like structurally for a more realistic example. Let's think about a multi-core system. And to keep this simple, I'll say we're going to try to prove this against a version of the ISA spec that just uses sequential consistency for the shared memory. First step we might take in our proof is say, well, our spec is multi-core system with sequential consistency. This will be kind of a functional program in its own right, a pretty short one. The length is basically proportionate to how many instructions we try to model. Our first step is to say, let's break that into one or more processors and a memory and prove that this multi-component system generates the same behaviors as the original version. Next key step, I take the processor at the spec level and replace it with a more optimized processor of some kind. And exactly what the optimizations are won't matter for this picture. Now we drill down into a subderivation to justify that step. Why is the fancy processor a correct realization of the spec level processor? Well, maybe first we do some sort of induction or simulation argument to show directly some other processor preserves the behaviors of the original spec. Then let's do another recursive decomposition of that processor and indicate it needs a FIFO in the design somewhere. So we'll break it up into the rest of the code plus the FIFO. Now we can do another recursive replacement and say, hey, you know, I have a ring buffer around that I verified. That is a correct replacement for an ideal FIFO. So it is okay for me to make this change within the larger system. So just recursively, we keep drilling down through the hierarchy of components, replacing pieces with others that we've proven preserve their behavior. At the leaves, we sometimes do explicit simulation arguments. And eventually, we get the whole optimized system proved correct with as much reuse of existing theorems as possible. So a key ingredient here for a processor is to have formal semantics for your ISA. Luckily, Nikhil just talked about this in some detail. We are using that kind of semantics to state the top-level theorem of a processor verification. Ideally, the same theorem should apply to many different RISC-V systems, so you don't have to worry that you accidentally convinced yourself your system was correct just because you had a typo in the specification. If we can reuse the specification across systems, then we can systematically avoid that worry. So what exactly have we done so far in terms of case studies applying this framework? We've basically constructed 2 RISC-V cores so far and 1 cache-coherent memory system. The first core that we built is basically a microcontroller class that only supports the user mode instructions but does run multi-core. And in progress now is a desktop class machine, 64-bit instead of the other one being 32-bit. And crucially supporting the S and M mode instructions so that we expect to be able to boot Linux on this thing. And we're currently debugging the specification so we get to the point where we actually know what it means to be able to boot Linux in a formal sense. But at least the specification that we have now does have approved implementation, which is able to run some prefix of the instruction stream for booting Linux. And we have a fairly sophisticated cache-coherent memory system with 2 levels of caches that we have proved. And like I emphasized early on, this is a proof for any number of caches, any sizes of the caches. All these kinds of parameters are handled once and for all by one theorem about the correctness of the memory system. So take that theorem, compose it with the theorems for either of those processors, at least in their finished forms, and you'll automatically get a full system correctness result that doesn't require you to know anything about how cache coherence works or the interface between the processor and the memory system. So the real promise of this approach is we and others who adopt the framework will build libraries of reusable components, processors, memory systems, whatever else, and then when you go to build a new SoC that has a number of accelerators on it, in addition to general purpose processors, you can write a specification for each of your accelerators, you can prove that the implementation meets it, and then you can seamlessly link with not just our existing IP blocks, but also their proofs, and get a complete system-level theorem about correctness. It isn't just testing or simulation-based verification. You can get a mathematical guarantee that the input-output behavior of your full system on a chip matches what you have also formalized as a specification. Of course, the proviso is you have to do extra verification work, writing out these proofs in ASCII to get this to go through, because everything's undecidable here. But we're trying to build the tools to make that palatable. So let me just wrap up with another potential consequence of doing things this way beyond just getting your SoCs right. So we have the formal semantics of the ISA at the center of the picture. We can implement a processor. We can prove that, considered as a piece of RTL, it does correctly export the formal semantics. However, we can also write some machine code that runs on the processor and give a specification for how we expect that machine code to work in terms of which input-output behavior it shows to the user. And that theorem can be stated in terms of the ISA formal semantics as well. So let's prove also that the machine code truly does implement the application specification if we assume that the ISA semantics is being provided from below. So what can we do then? We can link together these two proofs into a whole system result, where here by whole system I mean your RTL with this initial memory state providing some application and essentially some end user experience. We can prove the whole system truly provides that experience. And at this point, the so-called trusted computing base really shrinks, the opportunities for making mistakes in verification so that we accept an incorrect system. Where could we have some of those mistakes? We do still have to trust the general proof checking package that we're using, COC. We have to get the semantics right for RTL and for the application, but all these other massive artifacts fall out of the TCB. Bugs in them can no longer cause any actual bugs in the running system. We don't even have to get the ISA semantics right, because in some sense, the ISA has become an internal encapsulated implementation detail instead of the whole point of things if you just think of this as, let's verify a processor. Any bugs in the hardware design itself, whether written in Bluespec or RTL or whatever, cannot possibly survive in this process. The same is true for, say, the C code behind our application. There couldn't possibly be a bug in there that survives this process as long as we got the application specification right. So this is the real promise of this approach, which can really dramatically lower the cost of getting correct systems built and running. And for more information on this story, let me just end with a pitch for a larger project that I'm part of. It's called the Science of Deep Specification. It's a multi-university initiative sponsored by the American National Science Foundation. Our URL is on the screen here. We're working on implementing that whole picture I showed you, the software and hardware parts. We're running summer schools on a regular basis to explain these ideas to people who don't have any past formal methods experience. So for anyone who thinks this sounds intriguing, I'd invite you to go to that URL, join our mailing list, and watch for more information about our upcoming 2018 summer school, where we'll have hands-on training on both the Kami hardware framework I talked about and also on verification of C programs and how to plug these two pieces together. Thank you.